Okay, we are in chapter 8 now, section 8.1, and you're going to see that in this section and a little bit into some of the other sections, you're doing a big review of topics that were learned in chapters 6 and 7, namely how to find the 6 trig values by knowing their definitions. In other words, cosine can be defined using x and y's and radius as x over r. Tan can be defined as y over x. Cotan is the reciprocal of that, x over y. Sine's equal to y over r, and so forth. So we learned those definitions. We even learned how to define all of those trig functions by using SOHCAHTOA. So like for instance, cosine can also be defined, if you're thinking of SOHCAHTOA, as adjacent over hypotenuse, and so forth. This section also has a lot to do with those special right triangles that we concentrated on, and there were only 2 of them. There's the 30, 60, 90, and there's the 45, 45, 90. With the 30, 60, 90, always across from the 30 is the 1/2, always across from the 60 is square root of 3 over 2, with the radius being 1. 45, 45, 90, probably easier to remember because both legs were square root of 2 over 2, the x and the y, while the hypotenuse was 1. So there were those 2 special right triangles. Then when we got into chapter 6, we learned how to, instead of finding the trig values, we were finding the angles that were associated with certain trig values. And in some problems, we were doing a composite problem where we found the angle, and then we moved out to evaluate some other function, and then ended up finding the values on the leg. So that's a double problem. That's called a composite function. Some of that in chapter 7. But the main thing was using inverses to find an angle. So you'll see a lot of that popping up. So let's jump into the problems. This is problems 1 and 2, very similar. You are finding an angle, therefore you're reviewing things that you learned in chapter 7. Namely, if you want to find an angle, you can go from the non-inverse form, which is what you're seeing here, to the inverse form. And all that takes when you want to go from non-inverse to inverse is switching this number with the angle. They just swap places. So it's inverse of 2/5. So you can put that in your calculator, and you can at least show this for your work. Okay, then you're going to go into your calculator, quickly read what it is they want as far as the instructions go. They want the answer in degrees, so therefore you're going to need to change your mode in your calculator to degrees, and they want you to round it to 1 decimal place. So make sure you're paying attention to those instructions. So let me turn my calculator on. Okay, so let's check the mode. I'm going to go into mode. My mode is in radians, so I'm going to change it to degrees just by arrowing over to that word, pressing enter to make my calculator absorb that choice, and then quit out of this screen by pressing second quit. Okay, now we're going to put in the value that we're trying to get our calculator to do for us, which is inverse tan of 2/5. I'm going to press that right in. So second, all the inverses are second functions, then press in 2 divided by 5, close it up, and there we go in degrees, 21.8. Now if you recall, for inverse tangent, all inverses have restrictions, and the restriction for inverse tangent is anything from here, negative pi over 2, oops, no, this is positive pi over 2 to negative pi over 2. Anything from here to here. Okay, so when we just got an answer in our calculator of 21.8, note that that answer, 21.8, would have to be right in here. So we are well within the restricted area for inverse tangent. That is a review of what was in section 7.2. inverse tangents. Okay, moving on to number 2, which is just like the problem that we just did. You can get your calculator to assist you with this, although you might be able to do the finding the angle portion in your head. Many of you will be able to do that, but if you would like to do it the way we just did problem 1, you're welcome to do it that way. You're going to give your answer in degrees again, therefore your mode will be in degrees, and you can rewrite cosine as inverse cosine when you're looking for an angle. All it takes, once again, is switching this number with this theta. So square root of 2 over 2 is equal to theta. We're already in degrees. We can just go second inverse cosine. We're doing square root of 2 over 2. So second, to grab that square root symbol, it's square root of 2, close the parentheses, divided by 2. Close the parentheses again. And there you go. You get 45 degrees. If you recall, and let me write that right here before I give you a little review of section 7.1. If you recall, when we were learning about inverse cosine, the restricted area for inverse cosine is anywhere from here to here. And of course, 45 is right there. So we are well within the restricted area. Okay, when you look up at an object, the acute angle measured from the horizontal to the line of sight of observation of an object. You're looking at an object. So this is the horizontal. When you look up, let's say that there's a person looking out on the horizontal. And all of a sudden they begin to look up, up, up. Because they see maybe something up in the air, some kind of object. That is called, this angle right here is called an angle of elevation. Okay, that angle from here to here. Okay, and we'll do some problems that involve that, but right now we're just getting started. Okay, so moving on to number 4. We have this sort of problem. You can see, as I was telling you in my introduction to this section, that we were going to be pulling out a lot of the formulas that we were using in chapter 6 and 7, and of course we're going to continue to do that until the course is over. Find the value of each of the 6 trig functions. These are the 3 base ones, and then all you have to do is know who is the reciprocal of who, so that you can get the other 3 that are related to the first 3, but in a reciprocal fashion. So let's do sine first. Notice that this triangle is not complete. You've been asked to stand on theta, and you do need all 3 pieces of this triangle. So whenever there's a piece missing, with respect to the sides that is, you're going to be using Pythagorean theorem. So Pythagorean theorem goes like this. Hypotenuse squared is equal to leg squared plus leg squared. I'll just call this x. Okay, so in the calculator, 18 squared is 324, which is equal to 81, which is equal plus x squared. And then I'm going to subtract 81 from both sides. And get 243. Then I'm going to knock the square off of this by taking the square root of both sides. and I get 15.58. Now you have a decimal, and let's see what this says. Find the value of each of the sig. Use integers or fractions. Type an exact answer. That means I'm not allowed to give a decimal. Okay, so this is what we can do. Let's see if instead of using the decimal that we got, if we can give an exact answer, which is done by breaking it down yourself. So for instance, let's see, what's going to go into this 243? Maybe we can get a more simplified radical. 243 divided by 3. Okay, so we can break this down. I knew because it ended in 3 that 3 would go in here. So 3 times 81. And if you got a decimal when you tried to take the square root, is because there isn't an exact square root for this entire number, but there is for part of it. So that's called taking a partial square root. You can take a square root for this part, but not of this part. So taking the square root of 81, it comes out as a 9, while the 3 stays underneath because there is no square root of 3. This there is, it came out as a 9. So coefficient of 9, 3 underneath as the radicand, and the square is now gone. So now you know that this is 9 square roots of 3. Once you have every value around the triangle, you are then going to find the values. Now I want to be very specific here. When you are going to find all these 6 trig values, and you see that the theta is up here in the air rather than down here on the horizontal, you need to use SOHCAHTOA. Doing those definitions where the definitions are x over r, y over r, y over, it won't hurt you with the the y over x, but you should be using SOHCAHTOA whenever they move the theta, because usually the theta is measured between the horizontal and the hypotenuse, but now it's up in the air. So just to be safe that you're doing these trig values properly, let's practice using SOHCAHTOA. Remember that every 3 letters is a formula. This is the sine formula, this is the cosine formula, this is the tan formula. So when we go to do sine, it is opposite over hypotenuse. So we'll write the formula first so we get used to it and helps us focus. We will stand where they've told us to stand. Whatever they mention here, by the way, that's where you should be physically standing, because that is what determines what your opposite and your adjacent are, where you're standing. The hypotenuse is the hypotenuse no matter where you stand. It's the slanted side, the longest side. So if you're standing theta, this becomes the opposite. Whereas if you were standing here, it'd be something else. So position matters. So opposite is 9 square roots of 3, the one that we just found. Hypotenuse is 18. And then to get full credit on these problems, you have to know how to do the algebra that needs to be done in order to simplify it. Sometimes the algebra is as simple as reducing a fraction, as you see here. Sometimes it involves rationalizing the fraction, and that's more complicated. So here you're just reducing the fraction, 9 over 18. So just 9 goes into 9 once, 9 goes in here twice. Final answer, square root of 3 over 2. Now the minute that you do the sine, you might want to do the one that is reciprocally related to sine, which would be this. This and this are reciprocals. So if you found sine, you just need to flip that answer over in order to help you find cosecant. So it's 2 over square root of 3. As soon as you do the flipping, you see that you have an answer that's not completely acceptable. If you want full credit, you need to rationalize it. So if you multiply this by square root of 3, as well as the top by square root of 3. That'll float the radical to the top, which is it's allowed to be there, while rationalizing the bottom. Square root of 3 times square root of 3 is just 3. Okay, you can't reduce this coefficient, so here's your second answer. Let's go back up and do cosine, which we can get from this SOHCAHTOA formula. So cosine is adjacent over hypotenuse. You don't have to write it completely out like that. Adjacent over hypotenuse. Okay, so again, stand where where it says right here, whatever this angle is, that's where you should be standing. It should be your reference point right there. So you want adjacent. This 9 square roots of 3 is called your opposite. It is the side across from you, also known as the opposite side. The adjacent side will be the side that actually runs right into it, intersects with the vertex that you're standing on. See, this side has no contact, no intersection whatsoever with the angle you're standing on. But your adjacent side will always run right into where you're standing, and that would be this 9. Okay, so that's 9 over the hypotenuse, which is 18. Reduce it if you can, and you can. That reduces to 1/2. Think about who is reciprocally related to cosine. That would be secant. These two have a reciprocal relationship. So if you have already found one of them, all you need to do is form the reciprocal, which means flip it over to get the secant. When you flip 1 over 2 over, you get 2 over 1, which is just 2. So in getting one answer, you're really working your way towards 2 of them very quickly, especially when the other one doesn't even need any simplification as what just happened here. Okay, tan. Tan, again, let's look at SOHCAHTOA. It is opposite over adjacent. I'll just abbreviate the word adjacent. It's a little bit long for us to be writing out. Again, you're standing right here. Opposite is the 9 square roots of 3, while the adjacent is this 9, the leg that runs right into where you're standing at the theta. The 9s cancel. You're left with square root of 3, or you can look at that as square root of 3 over 1 because you are about to flip it over. Okay, so we have a 5th answer. Going in for the final answer, you know that tan and cotan are reciprocally related. So this flipped over, in other words, the reciprocal of this would be 1 over square root of 3. You do have an issue where you need to rationalize. So rationalize by multiplying by the square root of 3 on the bottom as well as the top. So now you have square root of 3 over 3. And that would be your final answer for cotangent. So that's finding the 6 trig values. Number 5 would be just like that. So let's see. I'll do a couple of these, but again, this is just like number 4. So I'll do a couple of these. Okay, so when you're doing the sine, again, I was just mentioning as I did all of these answers in problem number 4 that you need to stand wherever this theta is. That's your reference point. It's where you're going to position or locate yourself. And you should be using SOHCAHTOA for these. I mean, this one you could get away with the X and the Y type definitions. But I would use SOHCAHTOA on these triangles. When they're not positioned inside of a circle, just to be safe, use the SOHCAHTOA. So if I'm doing sine, that's going to be opposite over hypotenuse. You can show your work. You can write the formula. I just think that helps you to focus. Or you can jump into this answer, but show me something as far as what you're using for a formula. You can either write this or this. Okay, so if you're standing here, remember, stand on whatever the angle is that they mention here. Opposite would then be the side that's across from you, which is the 2. And the side that's called the hypotenuse is this right here, the slanted side. It's always located across from the right angle. It is the longest side. So hypotenuse is square root of 29. And if you take that, I mean, you can find the answer that goes with this, which is cosecant. You know that these two are reciprocally related. You could go ahead and flip that over right now, and you'd be into a second answer. Okay, the only thing is with this answer that we just got, I wanted to flip it over before I rationalized it because that'll save you a little bit of work. This, if you flip it over while it's at this state before you rationalize it, then you won't have to rationalize this answer. But anyway, this answer still needs a little bit of work. You need to multiply both the bottom and the top by square root of 29 to rationalize it. So it's 2 times square root of 29 over 29. That's that answer complete, and then you have this other answer. And likewise, you would do the same thing for the rest of these answers. I'll do one more pair. Cosine is, okay, according to this SOHCAHTOA, adjacent over hypotenuse. So that's going to be, let's see, I'm standing right here. This would be the adjacent leg. Again, notice that they're forcing you into a situation where you're missing one of the sides, and therefore when you go to do some of these values, you're not going to have what you need. So you might want to start any of these problems where one of the sides is missing on the right triangle with doing by doing the Pythagorean theorem, which will give you all the sides you need. So now that we have to, because of this problem that we are now, the value we're now doing, let's go ahead and do that, or you can just do it at the beginning. So I'll call this horizontal, I always call the horizontal leg X and the vertical leg Y if I happen to be looking for that. So the Pythagorean theorem that never changes, it's hypotenuse squared. The hypotenuse has to be on a side all by itself. Whether you put it on the left or whether you put it on the right, that's up to you, but there should be no other numbers with it when you first begin the theorem. I always put it on the left. So it's hypotenuse squared is equal to leg squared plus leg squared. Then go ahead and square everything out. You'll get 29 for the left. You'll get 4 on the right. And you'll get x squared right here. Subtract 4 so that you can bring it to the other side. That gives you 25 is equal to x squared, and then get rid of that square by taking the square root of the x squared term. So the square root dissolves this square, out pops the x, and if you take the square root here, you have to also take the square root here. So then you find out that this horizontal leg is 5. Okay, now continue with what I was doing. I wanted adjacent over hypotenuse, and what I was missing was adjacent. If you're standing right here, as you should be, that's called your adjacent, that's called your opposite. So adjacent would be 5, your hypotenuse, just as it always was, and even in part 1, is square root of 29. So 5 over square root of 29. And if you want to write the definition first, I'll do that just for consistency. It's 5 over square root of 29. And before I go ahead and rationalize that, I'll get the answer that goes with it. The reciprocal of tan is cotan. So by flipping this over, in other words, performing the reciprocal, you have 29 over 5. And that answer is perfect, but this one needs rationalizing. So you're going to multiply the bottom by square root of 29 as well as the top. That'll do what's called rationalizing or floating the radical to the top. And now you just have an integer, 29, whereas before you had an irrational number. This is a decimal that runs on and on. So we call that rationalizing. This is a rational number. Okay, so I'm not going to do the 5th and the 6th answer. That was 4 out of the 6. Let's move on to number 6. In number 6, you are being asked to find the exact value of sine of 67 minus cosine of 23. So in your theorems page, you're going to see that there are some theorems with regard to how to write trig functions with whatever value is next to them using what's called their complementary partners. So for sine, the complementary function, these are complementary pairs. You've learned about reciprocal pairs. So these are the complementary pairs. The complement is cosine. For tan, the complement is cotan. And for secant, the complement is cosecant. So what this theorem says is that anytime that you are using a complementary pair, what makes them equal is if you write one in terms of the other complement and you use the complementary angle. For instance, since sine and cosine are a complementary pair, you can start off with sine and any, whoops, went right off the page there. I'll just give you an example here with respect to this problem. You can start off with sine. They can give you any angle that they want, and as long as you are using its complementary trig function, which happens to be cosine, sine and cosine are considered a complementary pair. So you can write one in terms of the other, this is its complementary partner, as long as you're using the complementary angle. Remember, two angles that are complements, let me squeeze this in here, add up to 90. If you have forgotten what the word complements means. Add up to, that's called a complementary pair when the angles add up to 90. So what angle added to 67 would add up to 90? 23 degrees. See, these two angles are complementary angles, and these two functions are complementary trig functions. So that being the case, now that you know that, this is based on this theorem, and there's a few problems here in this outline that have to do with that. So now you can come in and you can either rewrite this trig function or rewrite this one. I'll rewrite this one, I guess. Okay, so its complementary trig function is sine. And if you're going to use the complementary trig function to cosine, you also have to use the complementary angle to 23, which is 67. In other words, 67 and 23 add up to 90. So cosine of 23 can be written as sine of 67. These two things are equivalent, just as it says right here. Almost like a substitution. It is a substitution. Now do the problem, because they're telling you to do it without a calculator, but you don't know how to calculate the sine of 67. But if you know that you are taking one value, sine of 67, and subtracting that very same value, it has to be 0. Anytime you subtract a value from the same original value, you end up getting an answer of 0. So by knowing this theorem about complements and how to rewrite them using complementary angles, you can calculate certain things without a calculator. Okay, so this answer, 0. Likewise, you can do this problem by understanding how to rewrite things in terms of their complementary partners. Like for instance, complementary partner to cosine, and you can either rewrite the top or rewrite the bottom. Don't rewrite both of them. Complementary partner to cosine is sine. Complementary angle to 69 is 21. In other words, what adds to 69 to give you 90? 21. So cosine of 69 is the same as sine of 21. You also have sine of 21 on the bottom. Now this problem has to do with division. Anytime you take a value, the value here being sine of 21, and divide it by the same exact value, your answer is 1. So without putting those things in the calculator, but rather using the theorems for how to write things in terms of their complementary partners, you are able to calculate the answer. Okay, doing number 8. In problem number 8, let's see, we have b is equal to 9. I'm going to go ahead and put these values right on the triangle. Let's see if I have a pencil here. So b is equal to 9. A is equal to 20. And let's see, if A is equal to 20, you also have you can also get this very quickly because these two are complementary angles. These are called acute angles when both of them are less than 90. They're called acute angles. So this pair is a complementary pair. So 20, this has to be 70. And you know that that's because the 3 angles inside of a triangle have to add up to 180. Well, this was already 90 that had been taken up by the right angle. So these two make up the other 90 degrees. And if that's 20, that has to be 70. So we also have angle B. And then we're supposed to find A, C. We already found that. We're supposed to find A and C. So you can do these problems. To start this problem, you need to be able to use your trig definitions, either SOHCAHTOA, or you can use those XY definitions. I would probably use the SOHCAHTOA, and I think I'm going to do that in this case. And you have to start the problem like that. And that's because of the 3 sides that are here, you only have 1. And that is not good enough for Pythagorean theorem. I know some of you are going to want to use that all the time, every time you're looking for the sides along the outer, the sides of the triangle. But you can't do that if you only have 1. You can do it when you get up to at least 2 of them, so you can get the next answer like that. We already found this one just by subtracting. We just went 90 minus, and you can put that for your work if you want, 90 minus the 20 that was given for angle A, which is how we got the 70. Then for, if I wanted to find side A, I could stand, let's see, I need to, if I'm going to use any of these trig formulas that we found, let's see, I could use opposite, and then I want the A in there. That means I'd be using opposite and adjacent. That's if I'm standing right here. Because if you're standing here, these things are called different. They're not called opposite and adjacent. See, from where I'm standing, the B value has to be called the opposite. And this A value, which is unknown, is referred to as the adjacent. If I was standing up here, that would be the reverse. So you have to be careful. Okay, so let's see. If I'm trying to stand on this 70-degree angle right on B, you can help me figure out what the trig function is. And if I want to use the one number that I do have, which is called opposite, it's opposite to where I'm standing. I'm standing right here on angle B. That's called opposite. And I also want to use the A, which happens to be called adjacent. Try to think of which trig function from SOHCAHTOA went opposite over adjacent. That was the last 3 letters of SOHCAHTOA. T-O-A. Tangent is opposite over adjacent. So that's how I figure it out. Just try to pick what things you want in the problem first. I wanted this 9 in the problem, and I wanted the A in the problem because I'm looking for A. Then try to ask yourself, with respect to where you're standing, what are the names of those things? That one's called opposite. This one's called adjacent. First decide what you want in the problem. I wanted these 2 things. Then decide what they're called. That'll help you to pick this. Okay, so let's see. So now I'm going to go tan of 70 is equal to 9 over A. I'll put that work right here. Let me clean it up a little bit without all this extra stuff. So just 9 over A. You're going to get this from your calculator. Make sure your calculator is in degree mode because you're pressing in a degree type number and looking for the tan. Okay, it's still in degrees. Let me quit out of there. I'm doing tan of 70, so tan of 70, close that up. And while you're in the middle of a problem like this, you're not on the last step yet, try to hold at least 4 numbers after the decimal. So I'm going to go 7475. Just for accuracy on that final answer. In the end, you can round to 2 decimal places, but well, you know, when it's your last step and you don't have any more steps left to do, then you can round to that. But while you're in the middle of it, be a little bit more accurate. Go out further. Okay, now when you're going to solve something like this, yes, you could cross multiply this way. You can do this using 2 more steps, or you can cut it down to 1 step. I'm going to teach you the shortcut. If you were doing this by cross multiplying, which even what I'm going to discuss with you, the shortcut is cross multiplying. You would multiply this A times this 2.7475. So you'd have 2.7475 times A. Then you would divide off the 2.7475 as your second step. Eventually, dividing both sides by 2.7475 and getting the final answer. However, one shortcut that you can use, and this is only to be used when what you're solving for is in the denominator. First of all, you can't solve for anything when it's in the denominator. It must be at the top level. So there's dealing with that, and then there's also dealing with getting rid of this 2.7475. You can do both of those things by just switching these two. Just let them switch places, and that'll bring it down to 1 step. You're bringing A up here, putting it in place of the 2.7475, and then where the A was, we're going to put the 2.7475. Okay, and then of course you're going to have to put it in your calculator and round it off. These little squiggly marks means I'm rounding it off. This problem has said to round it off to 2 decimal places. Okay, so putting this in the calculator, it's 9 divided by, I still have that answer in there, so I'm going to go second answer, which is the minus sign. You can just push second and then the minus sign, and you'll see on top of the minus sign, right down here, that it says answer. So that grabs the answer that was on the previous line and dumps it right in. It'll take the answer of the previous line, dump it right in there, if you don't already know about that, and there is the answer. Rounded to 2 decimal places, that means 2 numbers after the decimal. That would be 0.28, 3.28. Okay, likewise, we also have to find C. Now, at this point, it is up to you. You can now use either Pythagorean theorem, hypotenuse squared is equal to leg squared plus leg squared, or you can continue picking which is the trig function that's going to work in this particular case. Now, since this class is about trig, and you are trying to get good at trig, I'm going to go the trig route, because to me, it is less work. And it gives you a chance to focus on how do I pick, whether it's sine, cosine, tangent, or what have you, whatever you need for this particular problem. So let's practice what we are maybe not so good at yet. I already know you're pretty darn good at Pythagorean theorem. Okay, so let's say that I wanted to find C. If I wanted to find C, I need something from SOHCAHTOA that mentions hypotenuse. So you have the cosine definition. Remember SOHCAHTOA? I'll put it right up here. Look, the sine definition mentions the hypotenuse, and so does the second 3 letters. It mentions the hypotenuse. So either one of those is going to be good. Okay, now I'm trying to do, it's trying to get that hypotenuse, so I think I'll try to use, let's see, I have both of these legs already. Okay, so I'm going to use sine. Just make a pick. It really doesn't matter which of these two. Just use one of the ones that has hypotenuse, because you actually have both these legs, so it doesn't matter so much. Okay, so sine of, I'm going to stand on the 70-degree angle. You're welcome to stand up there, but then be careful. Okay, so if I'm using sine, definition of sine is opposite. I'm showing you every little step of what I'm thinking. This is where I'm standing. I've chosen the definition sine just simply because it has hypotenuse in it, and that's what I'm trying to solve for. So this is going to be, let's see, if I'm standing on the 70, opposite would be the 9 because of where I'm standing, and the hypotenuse is what it is. So I'm going to complete this by solving sine of 70 is equal to 9 over c. And just like I did the last problem, I'm going to get this from my calculator. So sine of 70 is 0.9396. And I'm going to leave that in my calculator, but I'll write 0.9397 as what it was. 0.9397 is equal to 9 over c. You're trying to solve for c, which is down in the denominator, just like this a was down in the denominator. And to go and to leave yourself with just one step to get to the final answer rather than two, you can accomplish that by just switching these two things right here. Just switch their places. The c pops up in place of the 0.9397, and this fraction now becomes 9 divided by 0.9397, which I'm going to put that in my calculator. 9 divided by, and then I'm going to take this answer, which is here, and just grab it by pressing second, and then answer, which is this key right down here. Okay, then don't forget to press equal. Now you can round it to whatever they've asked you to round it to, which is 2 decimal places, so 9.58. Okay, very similar to this problem is the next two problems. Number 9 and number 10, just like this problem, where you are deciding, which of the 6 trig functions to use to find the answers. You'll usually be given one answer just by one of the angles. So number 9 would be exactly like number 8, where you have one angle and that allows you to find the other one. You have one side and 2 left. So since number 9 is so similar to number 8, I'm going to skip to number 10. So number 10, notice that what is different about number 10, if you compare it to numbers 8 and 9, is that you don't have any angles. So let's go ahead and put these values where they belong. You'll have a much better chance of getting the problem correct if you put all the numbers right on the picture. So let's see, what do we have here? Oh, we just have 2 sides. We have a is equal to 1, and we have c is equal to 4. So you could get the third side. You can go Pythagorean theorem if you have 2 sides. So if we want to mix it up a little bit, I'm still going to do all of the trig function stuff, but let's go and find this time. I'll find that third side. You can use Pythagorean if you have at least 2 sides already. Okay, so you can go hypotenuse squared is equal to leg squared plus leg squared. Okay, this is 16, this is 1, this is b squared, subtract 1 from both sides, and you then have 15 is equal to b squared. You're going to take the square root of the right side as well as the left, so that you can have b rather than b squared. Okay, so now you can put that right here and continue the problem. So we have one of the answers, And that would be this one right here. I just get whatever one I think is easiest. And then let's go after the other ones. Okay, so as soon as we find one of these angles, either A or B, we can then just subtract to find the third one. Find each answer in the easiest way that you can. So now, let's see, I guess I'll go after, it doesn't really matter whether you go after A or B. Either one is entails the same type of work, where you're going to pick which of the 6 trig functions. So I guess I'm going to find B. I like to stand on the angle that's attached to the horizontal. So that's my choice, but you can find A as your next move. Okay, so let's see. How about if I use opposite and adjacent? Because if I'm standing right here, the square root of 15 is the opposite side. And I'm just making random choices because none of them are any harder than the other. You got to make a choice. You got to start somewhere. So this is opposite. This side right that's up underneath me that actually makes contact with where I'm standing is called adjacent. And if you are going to be standing on angle B and you're going to be using opposite over adjacent as the definition of the trig function. The trig function that's defined like this is according to Sakatoa. And again, here it is. These are the 3 different formulas. There's the sine function, the cosine function, or definitions if you want to call them that. Here's the tangent function. This is the one that I am using. Opposite over adjacent. So the name of the trig function is the tan. Those actual values in the problem are square root of 15 for the opposite. Adjacent has a value of 1. So it is tangent of some unknown angle is equal to square root of 15, or square root of 15 over 1. Remember, let's remember from section 7.2, when I want to find an angle that involves an inverse. So you go inverse, and when you want to go from the regular statement to its inverse form, from the non-inverse form to the inverse form, all that takes is switching these 2 things. You have square root of 15 right here is equal to the unknown angle if you're using the inverse. That's what allows you to find angles, which is what B is. So let's go ahead and clear out what we have here. We are in degrees right now. Pretty sure, yes. Okay, so we're going to go second. Inverse tan, put in what we have, which was square root of 15. So second, grab that square root symbol, that square root symbol, put the 15 underneath there. And then give it another parenthesis. This goes with this. We need one more parenthesis. And we have 75.5 degrees, but let's check out what they want as far as rounding, see if it says anything. Round to the nearest hundredth on the sides. Okay, so I didn't round that, but I will. Right now I'm doing an angle, and it says round to the nearest tenth, so 75.5. So this is 75.5 degrees. You have to round to where it says to round, otherwise my math lab marks it wrong. And then we're going to subtract from 90 to get this one, right? Because if this is 75.5 degrees, and you know that these 2 are a complementary pair, then to find this one, it's just 90 minus 75.5. 90 minus the other one. Okay, so I'll put that underneath here. 90 minus 75.5 gets you this answer. So 90 minus the answer that's still there, second answer, and it's 14.5. So 14.5 degrees. So I demonstrated Pythagorean theorem to start this problem off. That allowed me to find B, square root of 15. Once I did that, then I went into my first choice of a trig function. I decided to stand on angle B. That is your choice. You could have stood here or here. And I chose to use opposite over adjacent. you really had choices here because you did have all the numbers along the sides. So there were several ways that you could have gone in your second step here. I chose to do tangent because I was going to use opposite over adjacent. That allowed me to find angle B, and that's because I was standing on angle B, which made this the opposite and this the adjacent. So you were going after B. Calculator got me for B, approximately 75.5 degrees if we round it to the tenths place. And then to get the other angle, I just went 90 minus 75.5, and that got me 14.5. Okay, that is numbers 1 through 10. In the next video, I will do 11 through the end of this section.